Okay, if there are no questions, then we can just get right into it. I thought maybe we could start with just a review of what we've talked about so far, about how to solve differential equations. So just to recap, so far we've talked about second order, or let's see. So finding general solutions to a second order differential equation. We've talked about finding solutions to initial value problems. So for a second order homogeneous differential equation, so we have an initial value equals something. We've talked about finding general solutions to a homogeneous differential equation, or non-homogeneous. And then we want to talk about finding solutions to an initial value problem. Okay, so just to recap, right? So the first one, finding general solutions to the homogeneous case, you find roots of AR squared plus BR plus C equals 0. And then depending on what roots are, you get two linearly independent solutions. Right, so if there are distinct roots, right, you get e to the r1t, e to the r2t. If they're the same, you get e to the rt and t e to the rt. And if they're complex, you get these cosines. That should be it. So this is something we talked about, last week or so. Okay. Any questions on that? Just stop me at any point. So finding solutions to initial value problems, we do the same thing. Plug in initial values to above to solve for coefficients. Okay, so this was maybe last week or so. And then now we're on finding solutions to the non-homogeneous case. So this is non-homogeneous. This is the homogeneous case. Okay, and so we said that this comes in two parts. So you need to first find solutions to the associated homogeneous case. So just like for the homogeneous case, you find solutions, right? And then you need to find, so this is same as above. Right, but then you can add to that any particular solution to this non-homogeneous case. So all you need to do is find one solution to this, and then you can add it to any solution to the homogeneous case. So you find a particular solution. Basically by guessing and checking, right? By what's called method of undetermined coefficients. And we'll do some examples today. We did one example last section. which is essentially guessing and checking. Right, so if f is like a polynomial, you're going to guess a polynomial, and then you're going to plug it in and find the coefficients. If f is an exponential, you're going to guess an exponential and plug it in and find the coefficients. If f is a trig function, like sine or cosine, you're going to guess something like a trig function as well and plug it in and find coefficients. And really, in this part, I mean, this is maybe the part that's hard to remember, but there's a big table in the book that basically tells you what you should guess. I have not memorized that table, so neither should you. It's kind of used as a reference. So if you forget, you can kind of look it up. It's like, oh, we should guess this and plug it in and so forth. So we'll do some examples today on this. And then step 3 is you just add them, add them together. Add 1 and 2. Okay, and then lastly, finding solutions to initial value problems is you do same as above, and now you just plug in initial values. Plug in initial values. Do above to solve for coefficients. So really, this last one's like the longest process, right? Because in order to actually solve an initial value problem for a non-homogeneous case, you need to solve the homogeneous case. You need to find a particular solution to the non-homogeneous, and then you need to plug in initial values. So it's kind of like a lot of steps to going on. Very easy to make mistakes along the way. But this is the one we're going to do examples of today. And maybe also solutions to initial value problems. And then afterwards, we can talk about systems of ODEs. Okay, any questions so far? We can also go over any other questions on the homework, for example. Section's open. Otherwise, let's just start with an example. Okay, let's solve, let's see. Let's do an easier one. Y double prime plus, let's see, 2y prime minus 3 equals 2t plus 1. Okay, great. Let's solve this. So by solve, I mean find a general solution. Okay, and then we're going to do, after we do that, we're going to also find a general solution to, we're going to change this right-hand side to be various things as well. Let's maybe also do it equal to 3t. It will be another one. And we'll do some other examples. Okay, so let's start with this one. So according to our procedure, we should find solutions to the homogeneous case first, and then find a particular solution. So we look at the homogeneous case. We look at solutions. Did I do that? Yeah, I wrote it all right. Okay. We find roots. Okay, so this implies that we have two linearly independent solutions. You find e to the negative 3t and e to the t are linearly independent solutions to associated homogeneous differential equation. Okay. And the reason we do that is because it's going to affect, one, it's going to affect how we guess our solution for whatever is on the right-hand side, and two, it's going to change the general solution. So now we find the non-homogeneous. Okay, and we guess. And so we look at this right-hand side, we say, okay, that's a polynomial. And so a good guess for a polynomial is a function whose second derivatives, first derivatives, and itself will give you polynomials. And so we're looking for another polynomial, essentially. And because its degree is 1, um, only polynomials of degree at most 1 are going to give us, when we plug it into the left-hand side, will give us a polynomial degree 1 on the right-hand side. So we should guess particular solution is a polynomial of degree 1. So here's an arbitrary polynomial of degree 1. A and B, we don't know yet, so we need to solve for those. And so we plug it in. Plugging it into this differential equation, we get 0 plus 2 times A minus 3 AT plus B equals 2T plus 1. Right, and now we can just solve for coefficients. Right, we can compare coefficients on each side. So the coefficient of T has to be the same on each side. The coefficient of constant term has to be the same on each side. So in fact, we can even write it as a matrix equation. Right, comparing coefficients. Well, let's just not do that. Let's just, this one's easy enough, right? We can have 2A plus minus 3B has to equal 1, and minus 3A has to equal 2. So we get, I mean, if you want, you can write it as a matrix equation. And now we just solve, right? So we get that A is negative 2/3. B is whatever 1 minus 2 that is. 1 plus 4/3, 7/3, and then divided by negative 3. So negative 7/9 or something. This is where it's easy to make mistakes. But then we get that what A and B is, we get the general solution. So our final answer is the general solution is our initial solution, or sorry, our homogeneous solution. So C1 e to the negative 3t plus C2 e to the t plus our particular solution, negative 2/3 t minus 7/9. So any questions on that? So this is what the general solution looks like. If we wanted to find an initial value, or a solution to an initial value problem, so an initial value problem would have something like y of 0 equals something, and y prime of 0 equals something. And then we just would plug in 0 to t and set that equal to our first thing, and then take the derivative, set that equal to, set that, or input 0, and we solve for C1 and C2. Do you have to check your solution afterwards, or can you assume it works? Well, depends how much you trust your algebra. The age-old question: should I check my work afterwards? Yeah, you should. But I guess, or you can be confident that you solve for these correctly. But it's actually, I mean, this is only a second-order polynomial. It's not too hard to take the derivative of this twice and plug it in. So I mean, you could just check it pretty easily. It doesn't hurt to check if you have the time. especially now that we have 24-hour exams, it's, might as well check. Where can we find a table of guesses of homogeneous solutions? So I think you mean the non-homogeneous solutions. If I look at the book, for the non-homogeneous cases, I believe there's a table on page 178 called Method of Undetermined Coefficients, which essentially tells you what to guess in a bunch of these cases. So page 178 is, at least on the book, in the book I'm looking at, which tells you kind of what to guess. For example, let's do another, let's do e to the minus 3t as our right-hand side and see what might go wrong. Okay, so the homogeneous case is the same, right? You find two solutions, e to the negative 3t and e to t. And now we try the non-homogeneous case. So I'm gonna go to another page. We're looking at y double prime plus 2y prime minus 3y equals e to the negative 3t. And we found that the homogeneous case was e to the negative 3t and e to the t are solutions. Okay, now we're on the non-homogeneous. Okay, and so you might think, okay, let's e to the negative 3t. We should guess some e to the negative 3t. So maybe a good guess would be y of t, or our particular solution is some constant times e to the negative 3t. Because we're looking for functions whose derivatives, whose second, first, and derivatives in itself give e to the negative 3t, so it's something like a to the negative 3t. But when we check, we're going to find a problem. Right? If we were to plug this in to this left-hand side, what are we going to get? Right? We're going to get 0, because this is a solution to the homogeneous case. Right? A e to the negative 3t double prime plus 2 a e to the negative 3t prime plus a e to the, or minus 3 times it, it's going to be 0. And so we conclude, I mean, really nothing, right? We can't solve for a because we get 0 equals a e to the negative 3t. So we won't solve for anything. So, which is why you have to kind of amend your guess a little. Right, we shouldn't guess a to the negative 3t because that happens to be a solution to the homogeneous case. So we change our guess. And this is all in this table, right? It says like how to change your guess. You should change it by just adding an extra power of t. Somehow that makes everything work. So a to at. And now when you plug it in, you'll find that you can get a solution for a. And basically, you can just, whatever function you get on the right-hand side, you can kind of just look at that table and you can see like, okay, I should plug this in, and then you solve for the coefficients. So, okay, I'll do this one out. I mean, you need to take the second derivative of this. Is the first derivative. Second derivative. So you get okay, and so you can just take this and add 2 copies of this and subtract 3 copies of the original one and set that equal to e to the negative 3t. And you should get something for t. So you get Okay, and then you can compare terms on both sides. So the coefficient of te to negative 3t should be 0, and the coefficient of e to the negative 3t should be 0. Or it should be 1. Okay. Are there any other questions? Let's see, what do you get? You get negative 6a plus 2a plus 1, and then 9a minus 6a. So we can do another example, but essentially most of these are the same method, right? Solving these differential equations is not too difficult once you just kind of have what to guess, right? The steps are exactly the same. So the steps are, right, for any non-homogeneous case, you find solutions to the homogeneous case. Then you find a particular solution by these method of undetermined coefficients, which you can get by that table in the book. And then you just add them together. Oh yeah, so maybe we should finish the problem. Our final answer, so we shouldn't stop here, right? We wanted to find general solutions. So, right, our general solution is our answer is C1 e to the negative 3t plus C2 e to the t. That's our homogeneous one plus our particular one. Was there a question? Right, and then likewise, say you had some initial values. Let's say this equaled, I don't know, 5, and this equaled 2. Right, then you'd plug in 0 to here and set it equal to 5. And then you take the derivative, plug in 0 and set it equal to 2. And this would let you solve for C1 and C2. And if you want to be extra careful, you can always just plug this back into the differential equation and solve for it. You know, which you might as well do since you have 24 hours for the quiz, for example. Right, I forgot to say, there was a quiz today. Yeah. Should we do, okay, so maybe I'll pull the people here. Would you like to solve another one of these problems, or should we talk about systems of ODEs? Systems, okay. So I'm gonna go to a new page now. And we're gonna kind of switch topics a little. Well, not really switch, but we'll go on. We'll talk about systems of ODEs. Right, so now kind of going way back over here, right? Everything we did so far and everything we talked about, these are all for second order differential equations. For a single second order differential equation. But you can imagine differential equations that are higher order, or you can imagine differential equations that come paired with each other, right? So you don't have a single differential equation, but you have two paired differential equations, or three differential equations that come together that form a whole system. So for example, you might have something like x1 prime equals 6 x1 of t, minus 3x2 of t, right? You have x1 and x2, and x2 of t prime is something like this. Right, so this is called a system of differential equations because a solution to this is a pair of functions, which we usually wrap up as a vector. Right, so we're no longer solving for a single function, y. We're solving for simultaneous functions, or functions x1 and x2 at the same time. Right, and this is a system of two equations. You could feasibly have a system of n equations, just like we'd have a system of n linear equations. So this is a vector. Right, and so we can actually, wrap this up just as we did, 3 months ago. We can wrap this up as a matrix equation, and we get this matrix. Which is kind of a weird matrix, right? Because its values here, its elements are functions, which is something we've tried to stay away from before, right? Typically, our vectors have real numbers in them, but now our vectors have functions in them. So, and that's really just because we've now deviated from finite dimensional vector spaces, and now we're talking about these infinite dimensional vector spaces consisting of functions, and so it's kind of why we need to put functions in here. But right, we can wrap this up as a x of t equals x prime of t. Is a system, a linear system of ordinary differential equations, and it's actually homogeneous. Right? Because there's no extra term. If it was non-homogeneous, you'd have some extra functions that don't depend on x1 and x2. For example, you might have some like t here, or like a minus e to the negative 2t or something, right? And then this part would be floating around. You get a t and a negative e to the negative 2t. So the red would make it non-homogeneous. All right, so the question is, how do we solve these? Right, we can't just solve one at a time because the first differential equation depends on the second one, right? x1 prime equals 6x1 minus 3x2. Because x2, we don't know what it is. All we know is that it satisfies the second differential equation. But that second one seems to depend on the first one. So they're kind of hard to separate from each other. Right? So you can't just separate them. You can't just solve them independently. Well, at first glance, it seems like you can't solve them independently. But actually, if you pick the right basis, it looks like that. And then this matrix, when you write it in that basis, will represent a system of ODEs in which they are kind of independent from each other. Right? And so the answer, which I think was gone over in lecture yesterday, was we should diagonalize this matrix. So the answer, which I'll just kind of tell you the punchline now, is that solutions are given by eigenvectors and eigenvalues. And exactly how, well, let's do an example. And really the motivation behind this is that if you just look at ax equals x prime, or x is a matrix and these are vectors, but if you don't think about this as a matrix, maybe you think about this as just a real number, then a solution to this, a solution kind of is, quote, is just a first order differential equation, it'd be e to the lambda t. Would be, or like, I'll say C1 e to the lambda t, right? And then its derivative would be, so then the derivative x prime would be lambda C1 e to the lambda t. The reason I put this in quotes is because this is a vector, so really there should be vectors everywhere. So its derivative is just lambda times this, and then you get this eigenvalue equation, ax equals the derivative lambda x. This is equal to lambda x. And so that's why x should be some sort of eigenvector with an eigenvalue lambda. So that's kind of what we're looking for, is eigenvectors and eigenvalues. And so we should diagonalize A, is what we're going to end up doing. So I'll write this out again. We have 6, -3, 2, 1, x1, x2 equals x1 prime, x2 prime. So this is ax equals x prime. All right, and solutions, so we want to, let's diagonalize A, by which we mean let's find eigenvalues and eigenvectors, which we know how to do. So let's look at the determinant of 6 minus lambda, -3, 2, 1 minus lambda. And we get lambda minus 4 and lambda minus 3. And so we find that eigenvalues are 4 and 3. Because eigenvalues, remember, are solutions to this polynomial equals 0. Okay, so we find eigenvectors now. We look at 6 minus 4, 1 minus 4 equals 2, -3, 2, -3. So we find eigenvectors are 3 and 2, for example, or any multiple of this. Lambda equals 3. By the way, since we found 2 distinct eigenvalues for our 2x2 matrix, already automatically we know that A is diagonalizable. We don't even need to look at the eigenvectors, but we want them anyways. So we get 3 minus 3, 2, 2. Right, and now we can see that it's diagonalizable because V1 and V2 are linearly independent eigenvectors. Okay, and so the catch is the answer essentially is that solutions are given, so linearly independent solutions to this system of differential equations are e to the 4t times our eigenvector and e to the 3t times our other eigenvector. Right, and that's the takeaway. So that's how you solve homogeneous systems of differential equations. What we mean by this, by the way, right? Remember, these are vectors. What we mean by this is that a solution is a pair. Remember, a pair of functions, x1 and x2. So we mean that x1 has to equal 3e to the 4t, and x2 equals 2e to the 4t. If these are the functions simultaneously, this is a solution. Right, and also x1 equals e to the 3t, and x2 equals e to the 3t is another solution. Right, a solution comes in pairs now. You need to give both x1 and x2 because they need to satisfy this coupled system of differential equations. And if you want, you can plug that in, right? If you plug in 3e to the 4t and 2e to the 4t into your original system over here, if you plug in x1, if you plug in this is e to the, I already forgot what it was, e to the 3e to the 4t, and this was 2e to the 4t, then it should satisfy this differential equation. All right, so let's do another example. How did we know what to guess for the expression of x in the system of equations? In the system of, how did we know what to guess? You mean like, how did we know these are solutions? How did we get to linear? Basically, I'm just telling you that that's the answer. I haven't really like derived why this works, I guess, except that it, I mean, you can just plug it in and it'll work, right? If I just plug this in, you'll find that it's a solution. But basically, I'm just telling you the answer. The answer is just you find eigenvectors and eigenvalues and you form these as solutions. But I mean, if you want to prove this in general, then you can just, I mean, it's not too hard. You have ax equals x prime, and then you can just try to, you know, let v be an eigenvector with eigenvalue lambda of a, and then you can just show that e to the lambda t v is a solution. So this is maybe a proposition. Yeah, two questions here. How did we guess x equals c1 e to the lambda t? So that, like, this motivation over here, I didn't actually guess c1 e to the lambda t. This is, I solved the differential equation, right? This is, I solved the first order separable differential equation. Ax equals x prime. Quotes, I solved it, because A is a matrix, so I kind of pretended A wasn't a matrix. And then how do you solve, you know, ax equals x prime? You solve it, you get x equals c e to the lambda t. Or a, I guess there's at. I guess it should be c e to the at. A is nothing. It's just, this is all motivation. This whole thing should really be in quotes. This is like motivation, right? Like about why, you know, it's a non-rigorous hand-wavy motivation for why you should look at exponentials e to the lambda t. So it's why you should even consider like this exponential, this solution in the first place. But if you want to just skip the motivation, then you can just prove this proposition. You can just, if you have a matrix equation, ax equals x prime, let v be an eigenvector with the eigenvalue lambda, show that this is a solution. So you can just plug that in. Right, and then you get exactly so here's the question mark. Right. So that's the proof. And to answer a question before, a solution could be any one of those vectors, any sum of those vectors, correct. Yeah, So linear independent solutions are these, and so a general solution so a general solution is C1 e to the 4t 32 plus C2 e to the 3t 11. Right. So instead of now that with our system of ODEs, we have this extra kind of vector floating around. All right. So before we just had C1 e to the 4t and C2 e to the 3t, but now we have this vector 3, 2, and 1, 1 because we have a system. Why can you pull out the e to the lambda t? Just because 3 and 2 are constants, right? This equals 3 e to the 4t, 2 e to the 4t. In the next slide, again, just because this is just a, I mean, if you want, you can a e to the 4t 3 2. Right? These are all the same thing. Right, like A here is a matrix. You're multiplying it by 3 e to the 4t, 2 e to the 4t. I guess just the way it multiplies, e to the 4t is going to be multiplied by everything here. So you can compare this to the bottom. It's just kind of like a, since it's being multiplied by both of these, you know, you can bring it out everywhere. For the same reason that if I had something like A times, you know, 5, 3, 2, this would equal 5 times A, 3, 2. Right, like the 5 can also be brought out. So I think maybe the best way to get a grasp of this is to do another example. So why don't you try doing an example? Let's solve, you know, find a general solution to x1 of t equals x1 of t plus x2 of t, x2 of t equals x2 of t. This should be a prime. All right, I think that's the one I want to look at. Let's see. No, the other way around. Okay, why don't you try solving that differential equation? So this is a 2t. So you're going to want to write it as a matrix equation. You're going to want to find some eigenvalues and eigenvectors. And then you're going to want to see, find general solution. And then you're going to want to form the general solution. So I'll let you work on this for a few minutes and then we can go over it. And then that's basically what I wanted to talk about today. So you're also welcome to ask any other questions in the meantime. So I believe for the general solution, you get something like this, and then something like this. Great. You've now solved your first system of ordinary differential equations. Okay, so then in that case, you will conclude there. I'll stay on a little longer for more questions, examples, concerns, comments, etc.